Hi guys, welcome to a new video on differentiation under Math SL. In this video we shall focus on questions in the context of differentiation that feature mathematical models, real-life models. We shall be tackling the 4 questions on the screen in front of you, and I shall begin question 1 shortly. So question 1 came in paper 1, November 2004, question 11. Kindly take a minute and attempt to solve. The answer shall follow through shortly. So we are told that the population of bacteria represented by P is given at time t by the equation P equals 100 e to the power 0.05 t, which is rewritten right there in black. In question A, we are required to find the value of P when t equals 0. So this is very simple. I shall simply remove this t right there and plug in a 0. E to the power of 0 is 1, hence the answer is 100. So this is the initial population of bacteria. Population at time t equals 0. Now in question B, you are required to find the rate of increase of the population when t equals 10. So rate of increase is always given by dp by dt or dy by dx in general, and dp by dt is p dash, so I just need to differentiate this black equation right there. This is a simple chain rule differentiation. You should refer to chain rule videos if you don't know how to do this. So the answer is 5e to the power 0.05 t. Next, I need to plug in 10 instead of t, so I get 5e to the power of 0.05 times 10, which is 5e to the power of half, or 5 root e. So this concludes our first question on mathematical models in differentiation. I hope you have found it easy to understand. I shall begin question 2 shortly. Now would be a good time to pause if you would like to write the answer down. So question 2 came in paper 2, May 2010, time zone 2, question 7. Kindly take a minute to look through the question and attempt to solve. The answer shall follow through shortly. So in question A, you are required to find the value of n when t equals 0, given that they are related to each other by this equation, which is rewritten right there. N equals 800 e to the power of 0.13 t. So you're simply going to substitute 0 for t in question A, getting 800. Now in question B, you are required to find the rate at which n is increasing when t equals 15. Like we said in the previous question, to get the rate of increase, I need to get n dash. And n dash is given by 800 times the coefficient of t, 0.13, times e to the power of 0.13t, which gives us 104 e to the power of 0.13t. Next, I need to plug 15 for t into the derivative equation right there, and this gives me 731. Of course, this is a paper 2 question, so you can use the GDC to solve all of that. Now in question C, you are given that after k minutes, the rate of increase in n is greater than 10,000 bacteria per minute. And you are asked to find the value of k where this happens. So the rate of increase is greater than 10,000 is given by n dash is greater than 10,000. And we know from B that n dash is given by 104 e to the power of 0.13 t. But instead of t, I'm going to write k because this is the value of the time that I want to find out. So 104 e to the power of 0.13 k is greater than 10,000. I shall solve this algebraically. I shall isolate the exponent first by dividing by 104. Next, I shall introduce the len function to both sides to get rid of the exponent on the left hand side, and this gives me 0.13k greater than len 10,000 over 104. Next, I shall divide by 0.13 on both sides, and evaluating this on the GDC, I get that k is greater than 35.12. Hence, the least value of k, where k is an integer, k belongs to z, means that k is an integer. Hence, k equals 36 minutes. So take a minute to copy this down if you will. I shall begin question 3 shortly. So the third question that we shall tackle in this video came in paper 2, May 2014, time zone 1, question 5. Kindly take a minute to attempt to solve, and the answer should follow through shortly. So we are given that the population of deer in an enclosed game reserve is modeled by this function right there, where t is in months and t equals 1 corresponds to the 1st of January 2014. So t equals 1 corresponds to the first month of the year. We want the number of deer on the 1st of May, so May is the 5th month of the year, hence t equals to 5. So we shall substitute 5 into this equation right there. This shall give us 969.03, which of course we round down to 969 deer, because there is no such thing as 0.03 deer. Moving on to question B. We are asked to find the rate of change of the deer population on the 1st of May. So given that this is the function p of t, which I've copied from the question, I can get the rate of change by differentiating this function right there. This is a simple chain rule problem, and the derivative function is given by this red function right there. Next, I want to find the rate of change on the 5th month. So I substitute t with 5, and this gives me 104.5, which I then round down to 104 deer per month. So the rate of increase is 104. In question Bi, I am asked to interpret the answer to Bi with reference to the deer population size on the 1st of May. So the interpretation is that there were 969 deer in May 2014, and they were increasing by 104 deer per month. So this concludes our third question. Take a minute to copy this down if you will, and I shall begin question 4 shortly. So the fourth question that we shall tackle in this video came in paper 1, November 2007, question 14. Kindly take a minute and pause the video, attempt to solve, and the answer shall follow through shortly. So we are given that the area A kilometers squared which is affected by a forest fire at time t hours is given by this equation right there, rewritten in black right there. A equals A naught e to the power of kt. When t equals 5, the area affected is 1, and the rate of change of the area is 0.2 kilometers squared per hour. You are asked to show that k equals 0.2. So let's write down the given equations. We are told when t equals 5, a equals 1. So let's plug this into the black equation right there. So 1 equals a naught e to the power of k times 5. I've simply removed this a and plugged in 1. and removed the t and plugged in 5. So I get 1 equals a naught e to the power of 5k. Next, I use the second piece of information that I'm given, which is that when t equals 5, the rate of change of the area is 0.2. So first I need to find the rate of change of the area, which is dA by dt, or A dash, which I obtain by differentiating the black function to get the dark red function right there. So a naught e to the power of kt gives me k a naught e to the power of kt. Next, I plug in the given information, which is that when t equals 5, the rate of change is 0.2. Hence, 0.2 equals k a naught e to the power of 5k. And now I have two equations, both in two unknowns, which are a naught and k. So in order to solve for k, I shall simply divide the two equations by each other. I would rather divide the second by the first, but both techniques would work. If you divide the first by the second, that would work as well. Anyway, so I've chosen to use this equation in the numerator. So 0.2 over 1, I shall divide the left-hand side by the left-hand side, equals the right-hand side divided by the right-hand side. I've done this in order to eliminate all the repeated elements, and there are a lot. So a naught goes with a naught, and e to the power of 5k goes with e to the power of 5k. So you remain with 0.2 equals k. And this solves question A for us. So question B tells us that you are given that a naught equals 1 over e, and you want to find the value of t when 100 kilometers squared are affected. So from the unit of this number, we know that this is the area. The area is 100. So I want to find t when a equals 100 and a naught equals 1 over e, and knowing that k, which is a constant, is 0.2. So I shall simply plug all the known variables into this original equation and find the unknown variable. So I've rewritten the black equation, the original equation right there, and I've plugged in the associated variables, 100 instead of a, 1 over e instead of a naught, and the k I've substituted for 0.2. So 1 over e times e to the power of 0.2t is the same as e to the power of 0.2t over e. And since they have the same base and e is like e to the power of 1, so I can actually subtract the two powers from each other. The power of the numerator minus the power of the denominator. So 0.2t minus 1, even though the 1 is not explicitly written here, but we know that e is the same as e to the power of 1. Hence, we have reached so far that 100 equals e to the power of 0.2t minus 1. In order to get the t, I need to get rid of the exponent. I need to remove the exponential function, which I shall do by introducing the len function to both sides. So len 100 equals 0.2t minus 1. And I add the 1 to the left-hand side. Hence, t equals 1 over 0.2 times len 100 plus 1. Of course, 1 over 0.2 is 5, but if you don't know that, that's fine. It's perfectly fine to leave the answer as is, as the red answer at the bottom of the screen. So this is a perfectly fine final answer. Now this concludes our fourth question and this video. Take a minute to write the answer down if you will. I hope you have found this video useful.